Hello everyone, Namaskar, welcome to Math Guidance and welcome to the fifth lecture of chapter number 10, that is circles. Alright, we are going to focus on this topic, the cyclic quadrilaterals. Okay, and we are going to see two theorems based on these cyclic quadrilaterals, and then of course we are going to solve a few very good questions, very good examples, and this will be the last lecture of our chapter number 10. And in the next lecture we will see the question answer session. All right, so please be connected with my channel and please watch the video till the end. Thank you very much. So guys, let's start the topic, cyclic quadrilaterals. So what is a cyclic quadrilateral? All right, so the definition of a cyclic quadrilateral is a quadrilateral ABCD. Let's write it, a quadrilateral ABCD. Let us first draw it. Let us suppose this is the circle, this is the circle. So a quadrilateral ABCD is called cyclic if all the four vertices of this quadrilateral lie on the circle. Alright, suppose this is A, this is B, this is C and this is D. All the four vertices are lying on the circle. So this is called cyclic quadrilateral. So a quadrilateral ABCD is called cyclic if all the four vertices of the quadrilateral lie on the circle, itself, lie on the circle. All right, suppose this is a circle and you are drawing a quadrilateral like this, then this will not be a cyclic quadrilateral. All right, and suppose you are drawing a quadrilateral like this. Let us suppose you are drawing a quadrilateral like this. This is also not a cyclic quadrilateral. So the criteria is that all the four vertices should lie on the circle. All right, and a very important, very unique basically property of the cyclic quadrilaterals is that the opposite pairs of angles make 180 degree. So angle A plus angle C is equal to 180 degree. Also angle B plus angle D is equal to 180 degree. This is very unique property of cyclic quadrilaterals. All right, property of cyclic quadrilaterals. So if you try to do the activity, you can take any of the circle and the cyclic quadrilaterals, and if you measure these angles, this angle A and angle C, and you add, then you will find it nearly equal to 180 degree. So basically the either pair of angles are supplementary. You can also say either pair of angles, pairs of angles are supplementary. All right. Now there is a theorem based on this. Basically this is the theorem that the alternate angles are making 180 degree or are supplementary. We are going to study that theorem and its proof also. All right, and there is one more theorem that is the converse of that theorem. So first of all, let's study this theorem and its proof. Okay, so friends, let's understand this theorem and let's see its proof. The theorem is like this: the sum of either pair of the opposite angles of a cyclic quadrilateral is 180 degree, or in other words you can write it, the opposite angles of a cyclic quadrilateral are supplementary. Okay, so let's see its proof. All right, the proof, it's very interesting and very simple proof, very easy to understand. Let's first draw the cyclic quadrilateral itself. Suppose this is a cyclic quadrilateral. ABCD is a cyclic quadrilateral. A, B, C and D, cyclic quadrilateral. First of all, we will join this AC and BD, we will join it like this. Okay, so what are the given things? Given is ABCD is a cyclic quadrilateral. ABCD is a cyclic quadrilateral. Okay, and we need to prove is angle A plus angle C is equal to 180 degree. Also angle B plus angle D is equal to 180 degree. Alright. Now let's do one construction. Construction is that let's join AC and BD. Join AC and BD. Now the actual proof is here. Okay. So we will use the property that angles in the same segment are equal. Angles in the same segment are equal. This property we have already discussed and we have seen its proof also. Angles in the same segment are equal. Alright. Now let's take this one, AB, this segment. Okay. So this angle and this angle both are equal because of this property. Angle ACB is equal to angle ADB. Angle ADB. Also, let's take this one, BC. Okay. So this angle and this angle means this angle and this angle, they are also equal. Angle BAC is equal to angle BDC. Okay. Now in this triangle ABC, okay. Now first of all, let's add these two equations. So adding, we will get angle ACB plus angle BAC is equal to angle ADB plus angle BDC. Okay. So angle ADB plus angle BDC means angle ADC. We can write it, angle ADC. You can see from here, this angle plus this angle equal to this angle, angle ADC. Okay. Now in this triangle ABC, now in triangle ABC, we can write that angle BAC plus angle ACB plus angle ACB plus angle B is equal to 180 degree. We know angle sum property of a triangle. Angle sum property. Okay. Property of a triangle. So this implies this angle BAC plus ACB equal to angle ADC. Angle ADC plus angle B equal to 180 degree. And what is this angle ADC? This is basically angle D. So we can write angle B plus angle D equal to 180 degree, and this is proved. Okay. So simple proof. Now again we will use the angle sum property of a quadrilateral. This angle A plus B plus C plus D equal to 360 degree. Also we can write angle A plus angle B plus angle C plus angle D equal to 360 degree. Now we will put this one, angle B plus angle D 180 degree. This implies angle A plus angle C plus 180 degree equal to 360 degree. This implies angle A plus angle C equal to 180 degree. So both are proved. Angle A plus angle C equal to 180 degree, angle B plus angle D equal to 180 degree. Very simple proof. We are using this theorem, angles in the same segment are equal. So first of all we are using this segment, then we are using this segment, and we are adding these two angles, and we are getting this angle D after addition of this. So we are putting this angle D here in the angle sum property of a triangle, and we are able to prove this angle B plus angle D equal to 180 degree and angle plus angle C equal to 180 degree. Alright. So this is an important theorem. We have to remember it always. That is, sum of either pair of the opposite angles of a cyclic quadrilateral is 180 degree, or in other words we can write the opposite angles of a cyclic quadrilateral are supplementary. Alright. Now let's see its converse and let's see its proof also. Okay, let's move on. So the converse of this theorem is, if a pair of opposite angles of a quadrilateral is supplementary, then the quadrilateral is cyclic. Means angle A plus C or angle B plus D equal to 180 degree, then the quadrilateral is cyclic. Alright. So let's see its proof also. So given is a quadrilateral ABCD in which let us suppose angle B plus angle D equal to 180 degree. Angle B plus angle D equal to 180 degree. And we have to prove that quadrilateral ABCD is cyclic. ABCD is cyclic quadrilateral. This is what the converse says, is cyclic quadrilateral. Alright. So first of all, we will do one construction. Okay. The construction is little bit contradictory. We will let it that ABCD is not a cyclic quadrilateral. Okay. Let ABCD be not a cyclic quadrilateral. Let us suppose. Let ABCD be not a cyclic quadrilateral. Alright. Not a cyclic quadrilateral. So basically we will draw these two figures. One will be like this. So this A, B and C. Okay, A, B and C. And the fourth point, that is if this is in the extended portion of this. Alright, let us suppose this is the fourth point, D. Okay, and the second figure we will draw, it will be like this. Let us suppose this is the point. Okay, this is A, this is B, this is C and this is D. So ABCD is not a cyclic quadrilateral. Then if this is extended, then it becomes a cyclic quadrilateral. It becomes a cyclic quadrilateral. So let this point be D dash. Alright. So ABCD is not a cyclic quadrilateral, but ABCD dash is a cyclic quadrilateral. Alright. Now let's see. We have joined this one D dash A in both the cases, so that it becomes a cyclic quadrilateral. Now angle ABC, this one, in both the cases you can see angle ABC plus angle ADC is equal to 180 degree given. It is given here. Angle B plus angle D 180 degree. Also angle ABC plus angle A D dash C equal to 180 degree. This is the property of a cyclic quadrilateral. Opposite pairs of angles are supplementary. You can write it here. Opposite pairs of angles are supplementary. Okay, this is the property we have just now have gone through. Okay, now these are the two cases. That means right side is equal, so therefore we can write that angle ABC plus angle ADC basically is equal to angle ABC plus angle AD', and from here we can write that angle ADC is equal to angle AD', and this is only possible when this D and D' coincides. Okay, when this D and D' coincides, then and only then it is possible that these two angles are equal, otherwise it is not possible. Okay, so we can deduce that the circle is passing through ABC and D also. That means the quadrilateral ABCD is cyclic. So this is possible, you can write it, this is possible only when D and D dash coincide. Okay, coincide. Hence quadrilateral ABCD is a cyclic quadrilateral. Okay, so this is proved. The converse is also proved. Alright, very simple proof. Just the method of contradiction we have used. In the beginning we have supposed that this is not a cyclic quadrilateral, and then somehow we are contradicting ourselves, and then we are proving that this is basically a cyclic quadrilateral. Alright, okay, so let's move on. Let's see some examples, some very good examples. Okay, so let's see this example. This is a very good example in the sense that we will have to use so many properties in this question. Alright, so the question goes like this: in the given figure, AB is a diameter of the circle. AB is a diameter of the circle. CD is a chord equal to the radius of the circle. Alright, AC and BD when extended, this AC when extended and BD intersect at a point E. Okay, so we have to prove that this angle AEB is equal to 60 degree. Okay, so let's solve it. It's a very good example. Let's solve it. First of all, we will do one construction. We will join this OC, we will join this OD, and we will join this BC. Okay, why we are joining this? Because we are going to use so many properties related with triangles, lines and angles, and also of this chapter, circles. Okay, so we are joining this. So construction is like this: join OC, OD and BC. Okay, now let's take this one. Let us suppose this segment, this arc, let us suppose. So this angle COD, this arc, this angle COD and this angle CBD. So what we can write? Angle COD is equal to twice angle CBD, because we have read that angle made at the center is equal to double the angle made at another point of the circle by this arc. Okay, angle made at the center is double the angle made at any other point of the circle, made by the arc. You can write by the arc, okay, of the circle. We have gone through this. All right, now angle COD equal to twice angle CBD. Also, if you see, this is the radius, this chord is equal to the radius. So this is radius, and this is radius. That means this triangle OCD, also this triangle OCD is an equilateral triangle. OCD is an equilateral triangle because all the sides are equal, and sides are equal to the radius of the circle. Equilateral. Okay, therefore this angle all equal to 60 degree. So we are interested in this angle COD equal to 60 degree. Now COD equal to 60 degree, that means what? Angle CBD equal to 30 degree. Therefore angle CBD equal to 30 degree. Okay, CBD equal to 30 degree. Now one more thing we can see here. This is the diameter and this is making an angle here. So angle ACB equal to how much? Also angle ACB is equal to 90 degree. We have read it. Angle in a semicircle is 90 degree. Semicircle is 90 degree. Okay, we have seen its proof also. Now this is 30 degree, this is 90 degree. This is 90 degree, that means this angle is also 90 degree because it is making linear pair. So angle BCE is equal to 180 minus angle ACB, that is equal to 180 minus 90, that is equal to 90 degree. Okay, so this angle is 90 degree, this angle is 30 degree. So in this triangle BCE, we can easily calculate that this angle equal to 60 degree. So in triangle BCE, angle BCE plus angle BCE plus angle CBE and plus what we are required, angle AEB is equal to 180 degree, and this is angle sum property of a triangle. Angle sum property of a triangle. Okay, so this implies this is 90, this is 30. So this is angle AEB is equal to 180 minus 90 plus 30, that is equal to 60 degree, and this is proved. All right, so you can see how many theorems we are using here. First of all, this theorem, this is being an equilateral triangle, this property, this one, angle in a semicircle, this one, then the last one. All right, so it's a very good example. Okay, let's see one more example and then we will conclude this topic. Now let's understand the last last question of today's topic, today's lecture. So the question is, prove that the quadrilateral formed, if possible, by the internal angle bisectors of any quadrilateral is cyclic. Alright, we will solve it. We will prove it. Okay. By the internal angle bisectors of any quadrilateral. Okay. So let's take any quadrilateral like this: A, B, C, D, A, B, C, D, and the internal angle bisectors. Let us suppose this, and this. Okay. This is, let us take this point E, let us take this F, this is G, and this is H. Let us suppose this is making a quadrilateral here. EFGH is a quadrilateral formed by the internal bisectors of these angles A, B, C, and D. Okay. So let us write it. EFGH is the quadrilateral formed. EFGH is the quadrilateral formed by the internal bisectors of angles A, B, C, and D. Okay, and what we need to prove? We need to prove that EFGH is a cyclic quadrilateral. Let's see the proof. Okay, first of all, in this triangle, we can write this angle plus this angle plus this angle equal to 180 degree. So half of angle A plus half of angle B plus angle E, this angle E, equal to 180 degree. This is the angle sum property of a triangle. Angle sum property. Okay, property of a triangle. Alright, now let's come here. This angle is equal to this angle. Okay, so this angle FEH is equal to basically this angle E. How? These are vertically opposite angles. Vertically opposite angles are equal. Vertically opposite angles are always equal. This is a property from lines and angles chapter we have studied. Now this angle FEH equal to angle E. This angle E equal to how much? From here we can say angle E equal to 180 degree minus half of angle A plus angle B. We can write in taking common half, angle A plus angle B. Let us take this is angle equation 1. Now similarly we can write here this angle FGH. Similarly we can write angle FGH, that is equal to angle FEH equal to angle E and angle E equal to this. So we can directly relate from here. Angle FGH equal to, we can write 180 degree minus half of angle C plus angle D. Angle C plus angle D. This is equation 2. Okay, so this is equation 1, this is equation 2. Now let's add these two equations. Adding equation 1 and equation 2. Adding equations 1 and 2, we get, what we get? Angle FEH plus angle FGH. Angle FEH and angle FGH means this angle plus this angle is equal to 180 plus 180 means 360 minus, let us take half common, angle A plus angle B plus angle C plus angle D. We can write it, and now it's proved. 360 minus half of 360. This is the angle sum property of a quadrilateral. Okay, so 360 minus 180. 360 minus 180, that is equal to 180 degree. And now the opposite pairs of angles are supplementary, making 180 degree. That means what? That means this EFGH is a cyclic quadrilateral. Therefore EFGH is a cyclic quadrilateral by the converse of the theorem. What we have studied is a cyclic quadrilateral. This is a theorem, cyclic quadrilateral, proved. this is the converse which we have studied. So EFGH is a cyclic quadrilateral. All right. So it was a very good question. Hopefully you have understood it very well. So now let's conclude this this topic, and of course this chapter also. Only one lecture we will do for this question and answer. All right. So friends, we have seen this lecture. We have gone through two theorems related with cyclic quadrilaterals. One was the the opposite pairs of a cyclic quadrilateral make 180 degree supplementary angles, basically those are. And one is the converse, that if the angles are supplementary of a cyclic quadrilateral, then this quadrilateral is going to be cyclic, and we have seen its proof also. And then we solved two very nice questions, very nice examples we have seen, and in which lots of properties were being used. That is why I am saying it was a good question. So I hope you liked the topic and this chapter also, because the chapter is now concluded. Only one lecture is pending, that is the question answer session. We are going to see some very good, very nice questions in that lecture. Okay, so it's a nice feeling that 10 chapters have been completed. After that, one lecture which I will take in maybe tomorrow. So after that we will go to the next new chapter. Okay, so we will meet you in the next lecture, that is last lecture of this chapter number 10, that is circles. Okay, and thank you for giving time. Thank you very much.